Okay guys, I'm going to teach you about mutations today, okay, and keep it as simple as I can under the circumstances. We're going to leave a little bit out. So the homework that I'm assigning you will be in the textbook. What I'm going to suggest, okay, so the homework I'm assigning you finishes on page 345. If you are at all interested and you think you're going to go into genetics and take genetics second year, then I suggest you read pages 346 in the textbook to page, let me just see, 348, okay? So just an extra couple pages there. It wouldn't hurt you. I would normally assign that, but these are not normal circumstances. So these are the things you're going to need for this lesson. You're going to need page 11, okay, in your booklets. So you want to get that. You want to get page 38 in your booklets. It's going to look like this on the front, okay? There's a little comic on the bottom, and then you need your genetic code, which is on page 21. All right, so you're getting that, or you're pausing me, and I'm just getting a couple extra highlighters in case I need them. Okay, so let's go through mutations here. All right, so mutations are heritable changes. You know that. We're in the genetics unit, and we're talking about changes in DNA. Okay, so mutations are heritable changes. I guess we should highlight that because that's important. Organisms with mutations that cause their phenotypes under restricted conditions are conditional mutants. We're not going to worry about that. There are two types of mutations, okay, point mutations and chromosomal mutations. So what you want to know is that point mutations are what we're covering today, all right? We're not going to cover chromosomal mutations because we covered that in 4U or 3U. So in 4U, we step it up and I show you point mutations. This is your 3U information, okay? So I will give you a hint of what that is, but you should have some notes on chromosomal mutations already. And if not, I do have them at the bottom of this note, as you can see. So there are point mutations. What is a point mutation? It's a change in the sequence of your nitrogenous bases, okay? So one allele becomes another because of a small alteration in the sequence of the number of nucleotides or in the sequence of nucleotides. All right, so in other words, you're going to have a switch in nitrogenous bases, okay? So nitrogenous, oops, probably spelled that wrong, bases get switched, okay? So nitrogenous bases get switched. All right, so what you're going to need to know for this semester is there are 4 different types of point mutations, okay? So you do have to know each and every one of these. I'm going to take maybe 5 minutes and go over them with you. All right, so we start with a silent mutation. So this is what a silent mutation is. If you have a substitution in your DNA, okay, and it doesn't change the amino acid, then that's a silent mutation. Okay, so when we substitute one base for another and it doesn't change the coding of the amino acid, that's silent. Okay, so in other words, it's not going to be expressed. So genetic code, all right, how can we have a silent mutation? Well, what if once we made our mRNA or our original DNA, but I'm going to just go with mRNA because if I start talking about DNA, I'm going to confuse you guys looking at the genetic code. So let's say that our mRNA should say, once it's been transcribed, UCC. Okay, so I'm going to go with that today, UCC. Okay, you don't have to write this out because I'm probably going to erase it for the next time I teach you something. But let's say after transcription, the RNA should say UCC. But what if we make a mistake? What if the DNA is altered? Okay, so the DNA went through mutation, and then when it's transcribed, instead of saying UCC, it says UCA. Okay, is that going to make any difference for that amino acid? Absolutely not, because it's still coding for serine. So therefore, this is a silent mutation. Okay, so when you have bases when you have amino acids that have all 4 possible nitrogenous bases in the last position, and if it's only that base that's in the last position that is mutated, it's wrong, you're not going to get a mutation that's anything other than silent. Okay? And again, that's because of the redundancy in the genetic code. So if we change only the third letter, if that's where the mistake happened in copying, and all 4 possibilities code for the same amino acid in that third position, that's a silent mutation. Okay, missense. So a missense mutation means we're going to have a problem, right? So we get the mutation in the DNA, and the amino acid is different. So we have one amino acid being substituted for another, okay? So now, there was an assignment that I would give out in the past that would ask you, it would give you all kinds of mutations, and then it would say, is this person going to have problems digesting fat? I think it's actually the one I'm doing with you today. So where am I leading you here? What I want to tell you is that if there is only one amino acid that's incorrect in a whole chain of mRNA, likely it's not going to cause a major problem. It can, but likely it's just going to reduce efficiency, okay? So more often, you're not going to die from it. It's just your ability to make that protein is going to be reduced. And the protein itself obviously is going to be reduced in its capabilities because it's off a little bit, okay? Lots of missense mutations are obviously going to cause you a major problem, but tends to be that just one wrong base pair is not going to, do anything major. It's just going to, tweak you off a little bit. It's not going to be anything major. Okay, so nonsense mutations. This is the fun one for me. I don't know why I like these the best. A nonsense mutation is a mutation in your DNA, and when it's made into mRNA, it causes a stop codon in the wrong place. Okay? So in other words, we tell translation to stop at the wrong time. Okay? So the base pair problem results in a stop codon. And the last one is a frame shift mutation. So when we have a frame shift mutation, it means we're going to add or remove a base pair in the DNA, okay? So it's called frame shift because, for instance, okay, let's imagine that I have 3 A's and then 3 C's, okay? And this is my DNA. And let's say when we go through DNA replication that I add a C, okay? That shouldn't be there. So originally, I would have read it like this. This is the correct way, okay? But now when we're reading and we're going through and we're reading in this direction, oops, that's not a good one. Never mind. I'm not going to redo the video. So let's just change this up a little bit. And let me put a C there instead. Okay? So when we're going this way, this is how it was supposed to be, AAA, CCC. But then on accident, we added an extra C. Look what happens when we read that. Okay? So there's our first codon, and there's our second codon. Our first codon should have been AAA. Our second one should have been CCC. Oh, I said this was DNA. So then it would be UUU. G, G, G is what we should be reading, if that was our DNA sequence. And this is our faulty DNA sequence that's gone through a frame shift mutation. Why? Because I've added one extra nitrogenous base or nucleotide. And so when we read this, we have G, U, 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 G, G, okay? And that is different than this. This is correct. This is incorrect. So that's one way of having a frame shift mutation. The other one is to erase it, to get rid of one of those. So that would have been the better thing for me to do. Instead of adding that C, if we deleted an A, then we would shift what we're reading also. We would have had AAC, which would give us a different codon when we transcribe. Okay, so those are your different point mutations that you have to know now in 4U. Chromosomal mutations, if you're interested in a little review, they're all down here. Okay, so this is your 3U information. Deletions, we're going to lose a part of a chromosome. So after you cross over, okay, so crossing over occurs in meiosis 1. When these guys separate, what we would have is chromosome, let's say these are chromosome number 1, we would have chromosome number 1 taking a little extra piece of that chromosome number 1. So this one has a deletion, or sorry, this one has a deletion, this one has a duplication. Okay, so they work hand in hand. An inversion means when these guys separate. I didn't want to have to go over this with you and spend your time on this, but I am going to show you. Okay, so let's pretend that these guys, this is what I'm drawing. Okay, and I've got, let's say A, B, let's just do this, A, G, C. Okay, and we're going to cross over with another chromosome. And when these separate, if after crossing over occurs, when the chromosome gets its section back, let's say crossing over doesn't occur, but we've got a little bit of a flip that happens, okay, when it goes back. So instead of reading AGC, it reads CGA, okay? So now we've inverted this sequence as a result of crossing over, all right? So we have that happening, all right? A translocation means this. Crossing over could occur. This section could be lost altogether. And if this is chromosome number 1, let's say this ends up on chromosome number 5. Okay, now it's in the wrong location, and that's a translocation. Mutagens cause mutations. Okay, there are all kinds of mutations. You know that now. Some are silent, that don't even hurt you. And then carcinogens are chemicals that cause cancer in cells. Okay, so they cause mutations which cause cancer. All right, on the back, there's information about how we repair and how we find out if we have mutations. So proofreading I went over with you in DNA replication. Mismatch repair is something that happens right away. So we want this type of repair. So when we're looking at our new DNA after replication, okay, we find the problem right away. And so that's what I was showing you earlier in the DNA replication. So when DNA polymerase, and it's going to be DNA polymerase 1, notices that we have a mutation, it fixes it immediately. And it's based on methylated cytosine. Okay, and we even have that in here. That's based on methylated cytosine. So we know which strand is new and which strand is the template strand. If polymerase 1 doesn't find an error, doesn't find your mutation, then you still have your checkpoints that occur. And so you still have another chance to fix your mutation, and that's called excision repair. So excision repair is much more costly, okay, and it's going to say that in here, costly in terms of energy. So energetically, very costly, because you're not just fixing one mutation, you're cutting out a whole section of DNA. So if DNA were to read this, C, 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 A, and this is the correct strand, so this is our template strand, but we do this, G, C, oh sorry, that's correct, G, G, C, A, or not, I'm not going to do that. I'm sorry, guys. I'm working on not too much sleep today. This will be T, T, T. Okay, this is our template strand. This is our new strand. So we know that that's correct, that's incorrect. It's been missed by polymerase 1. And so excision repair says this, a whole chunk of DNA is going to get taken out. Okay, we're not just be able to fix this problem, we have to excise, which means to cut. Okay, so we're going to cut a whole chunk of DNA out there, and that requires more nucleoside triphosphates to power that machine. Right, so that's the end of that lesson. What I want you to do now is take out your genetic code and take out page, I can't remember what I said anymore, page 38. Okay, so this is what you're doing. I'm going to cover this up. Again, I'm not working a lot of sleep, so I figured these out before I actually videotaped today. Okay, so what we're going to do here, the purpose of this is to find out what kind of mutation do you have. Do you have nonsense? Do you have silent, etc.? So this is the DNA, okay? And so they're saying to us, in this case, this is the normal DNA to make a hormone that digests fat, all right? So what you're going to do, you're going to pause the video and you're going to come up with the mRNA sequence that pertains to this. So if you're unsure as to what I'm talking about, you're making mRNA. So you're going to say AUG, okay? So what I'm going to suggest is go ahead now and complete the mRNA sequences for all of these mutants. Okay, now you should be back after completing that mRNA sequence and have a look at mine, okay? So check yours versus mine. I think you can pause the video, but I'm not 100% certain. And notice this, okay? This is what I'm going to do with you. So this is the normal. This is the correct sequence that we're supposed to have. So if we look now at mutant 2, the mutation occurs right here, okay? So we've got, that's the beginning. How do I know that? For some of you going, how does she know that? AUG, GAG, these guys are all exactly the same, okay? When we get to this, this is where we have our problem. This doesn't say UGA, all right? And then we have a problem here as well, all right? And here as well. So notice, in addition, we have an extra nitrogenous base, okay? So we're going to get back to that one. Here we have everything is the same. What am I saying the same for? This one up here. Okay, so I'm comparing everything to the normal strand. And then when we get over here, this is where we have our problem. Okay, and then lastly, with our mutant number 3, when we continue through, we see everything is the same until we get over here. Okay. So I hope that helps with the highlighting. Now, what I want you to do is go through and come up with the amino acid sequence. So get your amino acid sequence for the normal hormone. Okay, and you're back. So this is the normal sequence for that hormone. I've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, and then this is stop, right? So that's why I don't put anything there, because there's nothing on that stop tRNA. It's just empty. So check yours. Make sure that yours is correct. Okay? So this is ideal. This is what we want. This is the correct version. Now, what we have to look at is what happened to mutant number 1. So mutant number 1, and I'm going to pull my genetic code out, okay? Because I'm going to work on this with you. And you can copy those if you want. And hopefully I'm not too sleep deprived to make a major error here. So we're good until we get to this. Okay, so everything is the same. But when we look at UGA, so genetic code, UGA codes for stop. Okay, so everything ends here. And so what kind of a mutation is this? Okay, think about the answer, pretend you're in class, and this is a nonsense mutation. So I want you to identify them. That's a nonsense mutation. Why is it nonsense? Because it codes for a stop codon in a place that should not be coding for a stop codon. Okay, so nonsense codes for a stop codon. All right, and that's why I'm coming up with that answer. So keeping that page 11 in front of you is also a very good idea. Now, let's work through this one. So I've got my amino acid sequence, met, glu, lys, ala, and I went all the way until I know that I had that mutation. Okay, so CAU is correct, CAC is incorrect. So, and I'm going to go back to this one because I did forget something with you. Those of you that are thinking right now, it's also a frame shift mutation. It absolutely is. So in number 1, this, we have an extra nitrogenous base here. If you look through here, it goes CAU, and then we should have another 9 nitrogenous bases, but we have 10. So that extra, the addition of that extra base in this DNA strand caused a shift, and that caused us to have a nonsense mutation. So if we're classifying this one, it's nonsense, and I don't have space here to write this, but it's also a frame shift mutation. So this one here is also frame shift because we've shifted the frame and we have an extra nitrogenous base. Okay. All right. So now we go to 1, 2, 3, 4, and our problem is here. So CAC, CAC codes for his. All right. And everything else is exactly the same. So here we have a silent mutation. It doesn't change the fact that we have that amino acid. We're supposed to have it. That's all good. All right. And then for our last mutant, we have everything the same. Okay. If we look at the normal mRNA, and we've got everything the same here, except when we get to here, I highlighted that. And so U instead of UGU, you can already see that because the mutation is on the second base pair, we know already that we're going to have a different amino acid. If it was the third, it could be silent, but it's the second, so it will not be. So U codes for phenylalanine, okay? And that's going to give us phe, all right? And then everything else is the same after that. So instead of having just his, we have phe, and then we have cis because that's the same, and then tyrosine, all right? So we've got those. This is no longer a silent mutation. This is a missense mutation. All right, so I'm giving you additional practice with those questions in the textbook. Starting tomorrow, going into Wednesday, I'm going to give you a quiz. It's going to be 10 marks, straight knowledge. So normally I would ask you guys to create these guys. I'm going to keep it very straight. I just want to make sure that you're understanding. And secondly, the reason I'm giving you another quiz is because that way the quizzes are not long, okay? And you're just, after we get quizzed, we leave that topic altogether, and unfortunately we're not returning back to it. So I think this is a good place to give you a quiz, because after this we head into restriction, enzymes, and technology, and that's going to be more thinking and application. So to get you a knowledge mark, I'm going to give you very straightforward questions, okay? And I'm thinking 10 to 12. I haven't made the quiz yet, but very, very quick, okay? Take care.